In this lecture, we're going to talk about the theory of electrical conduction in various materials. Metals, insulators, semiconductors, and even superconductors. It turns out that for a lot of these materials, such as metals, insulators, and semiconductors, we can use a single theory, unified theory, to determine, to explain why certain materials are good conductors of electricity, some materials are good insulators. This theory is called the band theory of electrical conduction. In fact, the band theory can be used to determine, to predict the electrical behavior, electrical conductivity. You can even predict what's called metal-insulator transition. In other words, sometimes we can turn a metal into an insulator and the other way around by changing what's called a band structure. So what is a band, or more precisely, energy band? And what does the band theory tell us? To understand where the band comes from, let's take a look at how we put atoms together in a solid. Starting with only two atoms, say for example hydrogen. We take the two hydrogen atoms. Each has an electron in its 1s energy level. The two 1s levels from each of the two hydrogen atoms has the same energy when they are very far apart from each other. Their electron clouds do not overlap. Okay. Now, as we bring them closer and closer and closer, we saw this example in our discussion of molecular bond, that the electron clouds will start to interact with each other. The result is that there are two possibilities, so-called bonding and anti-bonding case. In a bonding case, as you know, the two electrons, the two nuclei can get close together to form a stable molecule, because the electrons spend a lot of time in between them, so it's going to attract both of them. In the case of anti-bonding, here is one nucleus, here's another. The electrons spend very little time in between. The electron cloud probability is pretty much zero. And that is not favorable energetically, so they will not form a stable hydrogen molecule with what's called anti-bonding. So this is essentially useless if you're only talking about a hydrogen molecule. Now, the idea, however, is that when the two atoms get closer together, a single energy level, the 1s level, now split into two energy levels due to the anti-bonding, which is high energy, and the bonding, which is lower energy. Okay, so two 1s atoms splits, the two 1s levels split into two levels, bonding and anti-bonding. What if I have 3, 4? What if I have 100 atoms all linked together in a solid? Their electron clouds overlap. So what happens? Well, what happens is that the same energy level, 1s level, from say 100 atoms will now split 100 volts. Okay, will split 100 volts because of their interaction. And all these 100 levels will now be closely spaced together in between a minimum value and a maximum value. And you can see here that the energy spacing between one neighbor and one energy level and its neighbor is now considerably smaller than that, because we have to accommodate a whole bunch of them. Okay, 100. Now, what if I talk about a real solid where you don't have only 100 atoms, you have an Avogadro's number? Then what happens? Well, practically n approaches infinity, the number of atoms, and therefore the energy levels are incredibly close together because they have to split n folds. Okay, and as a result, the energy gap between one energy level and its neighbor practically shrinks to zero. Then we say you have a minimum value and maximum value for the 1s energy split n folds, but in between the minimum and maximum, the energy can be just anything. It's continuous. So therefore we say this is the energy band. This is the so-called 1s band. So you see, by tying all these atoms together, the 1s energy level, the discrete level, now expands into a band of energy. Energy levels essentially do not quantize within the band, so it's essentially a continuous distribution of energies. But the band, each band, such as this 1s band, has a minimum energy value and a maximum energy value. That is the idea of energy band. So as an illustration of this process, let's look at these diagrams. Again, using hydrogen as an example, here is the case of two hydrogen atoms. The 1s level splits into bonding and anti-bonding when the distance r between the nuclei gets smaller and smaller and smaller. And if you only consider the hydrogen molecule with only 2 hydrogen atoms, the nuclei will reach this distance or not, and they're gonna stop shrinking when they reach that distance. That's because the energy levels will be lowest here. Okay, this particular energy, which is the bottom of this curve, will now accommodate 2 electrons, one spin up, one spin down. So that is the energetically most favorable case. So case settled. They're going to form a stable H2 molecule with the nucleus to nucleus separation at R naught. Similarly, you can write the splitting for the 2s orbital. Okay, they have the same energy level between from each atom, and then you have the bonding case, you have the anti-bonding case. In the case of hydrogen, of course, these two 2s levels are empty because there are no electrons there. Here's the case with n equal to 5. You now have to consider a chain of 5 atoms all linked together. Their electronic clouds overlap, they interact. As a result, you're going to have a 5-fold splitting. Instead of a 2-fold, you have 5-fold splitting of every level. 1s now splits into 5 levels, 2s splits in 5 levels, and so on. And if you take that n equal to 5 to n equal to infinity, or at least, Avogadro's number, we're talking about an extremely large number, practically infinity, then the 1s energy levels will split into n levels within a very narrow region. And therefore, the energy gap between one level and the next level shrinks to practically 0. And the energy can be anything between the lowest level, lowest value, and the largest value. That is called 1s band. Similarly, you have the 2s band, and so on. So how far will the atoms come close together between nearest neighbors? Well, that depends on the overall electronic energy. You have to consider which part of the band is filled with electrons, which part is empty. For all the electrons for all the levels that are filled, as you get closer and closer, and see from here to there, as you get closer and closer, the atoms, some of the electrons will gain some energy benefit because they will push to lower energy. But some of the electrons will have to go to higher energy levels. Okay, so what you're looking at is the average or the mean value of the energy of the occupied electrons. Okay, of the occupied energy levels. Say let's say it occupies all the way to half of the band, which is the case for hydrogen. If you hypothetically think of hydrogen to form a solid, which it doesn't under normal circumstances, by the way. But if you did, then you can think of the 1s band as half filled because there are n energy levels within the 1s band, even though they're very close together. Each level can accommodate 2 electrons because of up and spin, down spin. But there are only n atoms, so each contributing 1 electron. So there are only n electrons. Fitting these n levels, each with 2 electrons, therefore only half, the lower half of this 1s band is filled, the other half is empty. So it's going to fit somewhere in the middle. So this is where the splitting is. Everything below that line would be filled, everything above that line will be empty. And then as you go this way in, what is the average energy of an electron in this band? For example, if the electron is here, if the distance of between nuclei is here, then you're looking at an electronic energy level, field energy between here and there. The average is somewhere here. And if you go to this energy, to this separation, then the electrons will fill energy levels between here and there, and the average will be this, right? Now you need to compare this average energy with that much average energy. Which one is lower? If it's lower, you're going to go this way. If it's higher, you're going to go that way. So it's going to automatically settle to a certain distance between neighboring atoms to minimize the total electronic energy. And that distance is not necessarily the same as this, because this only considers two atoms, not n atoms. There is no band structure here. There is a band structure there. Okay, again, as you put a whole large number of atoms together in a solid, you're going to form bands from each of the energy levels. And these bands can have a large separation between the minimum at the bottom of the band to the top of the band. For example, this particular case, the 1s and 2s, the 1s band can extend all the way up if if the particles are really close together. And you see here the bottom of the 2s band can be lower than the top of the 1s band. Of course, this case doesn't really happen in reality because you never go that close. The atoms will never go that close. But between 2s and 2p, that happens quite often. The bottom of the 2p band can, in fact, be lower than the top of the 2s band. That is entirely possible. Okay. Normally, 2s, 2s sits below 2p if it's a single energy level, right? But 2p can, now 2s expands up and down to form a band. 2p also expands up and down. So the bottom of the 2p may be here, but the top of the 2s could be there, could exceed the bottom of the 2p. So that happens. And it's very important that it actually does. We'll see why that's the case. So that is the idea of energy bands. So how does our theory of energy band help us understand why metals conduct electricity and insulators do not? We have to look at what happens when you expose an energy band to an electric field. If there's an electrical current flowing along the direction of the electric field in response to that electric field, then we say it's a good conductor. If that current is very small or zero, then we say it's an insulator. So let's see. If we expose a band of electrons to an electric field, what happens? Well, the electric field will accelerate these electrons, right? So we'll give it some kinetic energy. Because of that, the energy of that electron will pick up. Because it's being accelerated by the electron, will gain actual kinetic energy. So if you look at, here is one example. Here is a band, whatever band, 1s, 2s, 2p, whatever. This band is partially filled, okay, partially filled. And this is the highest energy of filled level, which is the Fermi level by definition. That's the Fermi energy right here. So the Fermi energy intersects a band, okay? It intersects a band. Let's look at what happens. Each electron, when you expose it to an electric field, will gain some more energy because of the additional kinetic energy it gets. So it's going to go up a little bit. Okay, it's going to be pushed up a little bit. So it's being pushed up from here to there. Can we do that? Yes, we can, because all these levels are still available. This is still within the same band. It's still available. You can actually go from here to there, no problem. All these levels are empty. You can go there without violating the Pauli principle. So this is a case of a partially filled band. When you put it in the electric field, the electrons will each go up a little bit in their energy, but it's still within the same band, so they can do that. So it will be a conductor. It will contribute to the conduction of the electric field, electrical current. Now, what if you have a case where all of the energy bands are either completely empty, like this case, or completely filled, like that case? If the band is completely empty, there are no electrons there. Therefore, you put that band in the electric field, nothing happens because there's nothing to do anything. Okay, no electrons. What about a completely filled band? A completely filled band, an electron, say an electron's here. Okay, you put it in the electric field, so it says, okay, I want to accelerate. I want to gain some more energy, so it wants to go there. Can you really do that? No, because this final destination is already occupied by somebody else, right? It's occupied by somebody else. Unless this is empty, you cannot do that. What about an electron at the top of this band? Well, if it gets a little bit of energy from this electric field, it can go up to there, provided there is something there to accommodate that electron. Is there an energy level there? No. Within each band, you can assume any energy you want, as long as you do not violate the Pauli principle. But between the top of one band and the bottom of the neighboring band, there is a gap. There is nothing in between, no electronic energy levels in between. So therefore, the electron cannot be pushed to here because there is no state available there. The only thing you can do is to give it enough energy that goes all the way across the energy gap. And what if this energy gap is so wide that electrons simply cannot get that much energy from the electric field? Then, too bad. The electrons cannot go this way, but it cannot go that way, so they just don't do anything, which means they cannot contribute to electrical conduction. So you see, a completely filled band behaves the same as a completely empty band in the sense that because of the Pauli principle, you put it in the electric field cannot possibly do anything. It cannot conduct electricity. Except in the rare case where the electric field is so strong that literally pulls these electrons all the way across the gap so that it goes into the conduction band. So now you simultaneously created two things. You have created a partially empty valence band and a partially filled conduction band. So both of these bands become partially filled, and therefore both can contribute to electricity, to electrical conduction. And this happens only when the electric field is incredibly large. And we can understand that, you see, because if you take an insulator, right? If you expose this insulator to an extremely strong electric field, what happens? It turns itself into a conductor, right? I mean, this is when we say it breaks down, right? You can understand why it breaks down because, again, you have enough energy to take the electrons all the way across this gap. So if the gap is large, that's almost impossible to do. But if the gap is small, that'd be possible. That may be possible. Okay, so we introduced the concept of conduction band and valence band. What is the valence band and what is the conduction band? In the case of an insulator, the conduction band, the valence band is the band with the highest energy that, or right below the Fermi energy that is completely filled. Okay, is the band with the highest energy that's completely filled. What about the conduction band? It is the band with the lowest energy that lies above the Fermi level so that it's empty. The lowest empty band. Here is the highest filled band. There is no partially filled band, and therefore there is no band of electron that can contribute to electrical conduction because of the Pauli principle, and therefore it's an insulator. A metal has at least one partially filled band, and this band, the electrons in this band can contribute to electrical conduction. So therefore the Fermi energy must intercept at least one band. It's not in the forbidden gap like in this case. Okay, so how do we define a metal? Well, there are chemical definitions. In chemistry, define metal as, in terms of electron affinity and so on. But in solid-state physics, here's how we define a metal. A metal is an elemental form of substance such that the Fermi energy intercepts at least one band. Okay, sounds funny, but actually this is a scientific definition. It tells us why metals can conduct electricity. So you see, we can actually predict whether something is going to be an electrical conductor or an insulator depending on the band structure. In other words, you have 1s band, 2s band, 2p band, and so on. That's called a band structure. And where is the Fermi energy? The Fermi energy in this case is here. So it's filled. All these energy levels are filled, and there is one partially filled band. Okay, that partially filled band in the case of metal is the conduction band. In the case of insulator, there is no partially filled band, so the first empty band is called conduction band. So here we have a conduction band. There is a reason we call it conduction band because obviously this is the one that contributes to electrical conduction. It is a 3s band in this particular case. Okay, so when you put this material in the electric field, the 3s electrons in the 3s band can conduct electricity even though those guys don't do anything. This, of course, is the energy band structure of sodium. You see, sodium, the highest field energy levels are the 3s energy levels. So these electrons, the 3s electron will form a 3s energy band, which is partially filled only. Okay, you see, we have arrived at a very important conclusion. Electrical conduction in solids is determined by the band structure. I should say crystalline solids. Otherwise, you don't have this definitive band structure if it's amorphous. Electrical conduction in crystalline solids is determined by band structure. So in solid-state physics, one of the most important things is for us to determine the band structure so we can then figure out what kind of electrical conduction property it has. We can look at examples of lithium, beryllium, sodium, and so on. This is sodium. We can see why sodium is a good conductor. Okay, lithium, very similar. Lithium has two 1s electrons and one 2s electron. So the 2s band in lithium is half filled. Right? It's half filled. And therefore, the 2s band is responsible for electrical conduction in lithium. Lithium is also a good conductor. Now this guy, beryllium, is a little bit interesting. Beryllium has the element beryllium, the atom has two 1s electrons and two 2s electrons, right? The atomic number is 4. So two 1s electrons, two 2s electrons. And if you believe that energy, that the band structure of beryllium looks like this, then should it really be a conductor? It looks like it shouldn't, right? Because, 1s band is completely filled, 2s band is completely filled, here's 2p, there's a gap. Okay, so these levels are completely filled, these bands are completely filled, those are completely empty, there's a gap. So beryllium is supposed to be an insulator, and yet we know beryllium is a metal, it's a conductor. What is going on here? Is our theory totally wrong? No, our theory is correct. If you want to be a metal, the Fermi level, the Fermi energy must intersect at least one band, which means there has to be at least one partially filled band. What is going on? It's just like what I said before. Okay, the band structure is different. It turns out that the bottom of the 2p level actually is lower than the top of the 2s level for beryllium. This is not the energy, the band structure for beryllium. You got to know how to calculate the band structure if you want to make accurate predictions. Okay, so the bottom of the 2p is somewhere here, and the top of the, so 2p is like this for beryllium, and the top of the 2s is higher than that. So that means that some of the 2s electrons will spill over to 2p, which makes the 2s partially filled and the 2p also partially filled. You got two conduction bands all in one. One from 2s, the other from 2p, because the band overlap. So again, it is the band structure that determines the electrical conductivity. All right, so this is what makes the difference between metals and insulators when it comes to electrical conduction. We use the band theory to determine that. But what about that mysterious material that's somewhere in between? Not good conductors, not good insulators, but somewhere in between. What is that? It's called semiconductors, right? Now, semiconductors are of great interest, and their importance is beyond words, because, without semiconductor, there won't be any modern electronics. Computers, iPods, all of these things that we take for granted, every piece of modern electronics will not have existed without semiconductors. So what is the big deal about semiconductors? Why are they so incredibly useful to us? What kind of role does it play in microelectronic industry? Let's look at some essential physics behind the amazing properties of semiconductors. When we talk about semiconductors, essentially we're talking about these two elements, silicon and germanium. They both belong to group 4. So they're not very good conductors, they're not very good insulators, somewhere in between. Why are they so incredibly important? Well, let's start with what's called intrinsic semiconductors. This is basically a pure piece of silicon or germanium with no other atoms in it. It's pure, chemically pure. The energy gap between the conduction and valence band for an intrinsic semiconductor is around 1 eV. Now, for a good insulator, it's several EVs, like 7, 8 EV. But for semiconductors, it's actually 1 EV. If you do not consider the thermal excitation of electrons across the gap, across this energy gap between the valence and conduction electron, then basically semiconductors are supposed to be insulators, because the band structure is such that the valence band is completely filled, the conduction band is completely empty. The only difference between intrinsic semiconductors and insulators is that this energy gap, again, is relatively small. It's about a factor of 10 smaller than good insulators. It's only about 1 eV. For silicon, in fact, for silicon it's about 1.1 eV. For germanium, it's even less, like 0.7 eV. What does that mean? It means that because the gap is not very wide, even at room temperature, it's not that hard for an electron at the top of the valence band to jump over, to gather enough energy to jump over to the bottom of the conduction band. Thermal excitation. The probability of that happening is governed by the Boltzmann factor, e to the negative energy gap over kT. Okay. The energy gap, again, is about 1 eV, not 10 eV. And kT is about 1/40th of an eV at room temperature. So it's e to the power negative 30 or 40. You think it's very small. It is very small, but we're talking about Avogadro's number. Okay, we're talking about Avogadro's number of electrons. So even though the fraction is very small, there's still a significant amount, total amount of electrons that can actually make their way across the gap only through thermal excitation at room temperature. So that makes them a little bit conductive, even though they're not very good conductors. That's called thermal excitation. It can also receive energy from a photon. If a photon comes in, the photon with an energy of at least equal to energy gap, so it's infrared or above, then that photon will carry that electron all the way across the gap, so it becomes conductive. So you see, intrinsic semiconductors can change their conductivity dramatically according to temperature and exposure of light. When the temperature gets higher, when T gets larger, this probability dramatically increases exponentially, which can turn the conductivity up several orders of magnitude. Okay. Also, when you expose this to light, you can then look at, you can imagine energy transfer from photons to the electrons to carry them across the gap, so they can become better conductors. So they can be used as heat or light sensitive instruments. For example, if you want to build a device which controls your thermostat, which controls your air conditioner, so it turns itself off automatically when the temperature is low enough for AC, and when the temperature is high enough, it turns itself on. You can use a semiconductor sensor because the electrical conductivity changes dramatically as the temperature changes. So you can use that to control the on and off of the AC unit. Now, when it comes to electrical conduction in semiconductors, if there is no electrons crossing the gap, again, it's an insulator. You have zero conductivity here because everything's filled. You have zero conductivity there because there are no electrons to begin with. If some electrons make their way across the gap, then it's going to leave behind, they're going to leave behind some vacant spot, right? These vacant spots are called holes. Holes can conduct electricity just like electrons can. So when you expose this semiconductor to an electric field, okay, to an electric field, let's say the electric field points this way, a electric field points this way. Both of these bands will contribute to electrical conduction, but they behave differently, in a different manner. In the conduction band, you got actually some electrons coming from here. These electrons will move opposite to the electric field. In the valence band, you have these holes or empty sites. They will move along the direction of the electric field. So a hole behaves like an electron going backwards. So it behaves like a positively charged particle. You see, a positively charged particle going this way is the same, is equivalent to a negative charged particle going that way when it comes to contributing to electrical current, right? So how do you understand the idea of this hole? A hole, again, is a vacated spot. Okay, it is where there was supposed to be an electron, but the electron is missing because it went up. I can understand the behavior of a hole from this diagram. Imagine you have a traffic jam. Okay, so each of these black arrows indicates a car. The car is supposed to be moving this way. And let's say at one particular instance, there is a spot, empty spot between these two cars. And when this driver sees a spot, what does he do? He pulls himself forward to fill this spot, right? So he is now here. And then that empty spot is now there. It's vacated by that driver. And this guy, immediately after him, sees this spot. So what does he do? He goes forward too, and then his spot became vacated. So as the cars go forward, the empty space travels backwards. You see that? So if you imagine each of these cars as an electron, so as the electrons travel forward to fill that hole, the hole itself travels backward. That's equivalent. So instead of saying electrons travel this way, we can say a positively charged hole traveling backwards. That's equivalent. So when electrons can conduct electricity, the holes can do that too. So here we have a case of an intrinsic semiconductor with electrical conductivity coming from both the electrons in the conduction band and the holes in the valence band. So at this point, there doesn't seem to be that much of an interest in semiconductors, besides the fact that it can be sensitive to heat and sensitive to light. But other than that, why are they so incredibly useful? Well, it turns out is because of combination of things. First of all, even though intrinsic semiconductors are not the best conductors or not the best insulators, their electrical property, such as electrical conductivity, is tunable. Unlike metals, which are always good conductors, insulators, which are always good insulators, a semiconductor can have electrical property, such as conductivity, that varies by many orders of magnitude according to how we adjust it, how we tune it. It's an extremely tunable material. The way we tune the electrical conductivity is through what's called doping. Here in this context, doping is a good word, not a bad one. Okay, we'll see how we do that. And also, it will lead to some of the most interesting characteristics, voltage amplitude, voltage amp characteristics, which means when you apply a electrical voltage to the device, semiconductor device, how does the current behave? It's called VA characteristics. Very different from traditional Ohm's law. The device is called a diode. And they can also be used to form the basis of modern solid-state amplifiers. An amplifier is an element in electronic circuits which amplifies an electrical signal. The incoming signal has a low potential difference. The output signal has a higher potential difference. That's called amplifier. And the device is called a transistor. These things are just everywhere in modern electronic circuitry. So that's what makes semiconductors so incredibly important.